Hi everyone, welcome to the second module for the Intro to Neurotech crash course. If you've gone and watched the first module, we covered the basics of EEG data analysis, and the functions and parts of the brain. The second module is focused on frequency domain and signal processing. And what we particularly focus on in this module is understanding how we go from collecting electrical data in the units of milliseconds by microvolts and converting that into frequencies, and what these frequencies are ultimately useful for in terms of telling us what the brain is doing. As a bit of a roadmap, we'll first cover the frequencies themselves, the different types of frequencies and what functions each frequency is associated with. And then we'll cover three main things: fast Fourier transformations, PSD plots, and filtering, all of which are relevant for signal processing in terms of not only brain-computer interfaces, but just broader neuroscience in general. We'll then release another video that goes over how to analyze data in Python and how to apply some of these frequency analysis techniques using Python and visualizing them in Jupyter Notebook. So a lot of people, whether they come from a neuroscience background or not, are already familiar with brain frequencies. A lot of people have already heard about alpha waves and beta waves, but what exactly are these frequencies and what do they tell us about what the brain is doing at that particular time? So there are four main frequencies in the brain, and they operate at different frequencies. So you have the beta range, which is 13 to 30 hertz. You have the alpha range, which is 7 to 13, and so on and so forth, as you can see on this image. These frequencies are not hard cut. It's a bit of a loose range, in my opinion. It's not like if you're at 14 hertz, you're not at the alpha range at all. So there is a bit of a margin there, but roughly, the alpha waves are referred to as any frequency that is between 7 to 13 hertz in the brain. And so each of these frequencies are associated with different activities in the brain. So beta waves are often present when we are awake, when we are thinking, when we are excited, when we're trying to actively focus on a task and trying to complete that task. Alpha waves reflect passive mental activity. So whether you are zoning out, whether you are just closing your eyes and sitting there, these kinds of passive mental activity or passive states of being are associated with alpha wave activity. Theta wave activity has been known to be induced when you're undertaking creative tasks or when you're kind of self-reflecting also. And delta waves are only present when you're in deep sleep. And delta, I guess, is the slowest wave that occurs in the brain, and you can really tell that there's very less activity going on. And so you only see delta waves when you are in deep sleep. So we have these types of frequencies that can be categorized in different bins in terms of their function. But I think a common misconception that a lot of people have is that there's only one frequency present at any given time. And that's not true. So if you were to collect EEG data from my brain right now, you would probably find all of these frequencies to some extent, except delta. And what that shows you is that it's not which frequency is present in the brain or which frequency can be noticed from the data. It's the extent to which the frequency can be noticed. So all these frequencies are there. We have beta waves, we have alpha waves, beta waves, but the power of each frequency and I guess the extent to which it's present is what makes the difference in terms of what we want to extract from the data. And I'll touch upon this later in the video as well, so it'll make more sense when you actually look at a sample piece of data. But keep in mind that it's not an absolute thing, like it's not a binary thing that whether the frequency is present or not. So it's not 0 or 1. It's a gradient scale of like how much of the frequency is present or to what extent the frequency is present amongst all of the other frequencies in this data set. So we covered, in the first module, we had this image as well, and we basically covered how EEG data collection works and how you get electrical signals and why you're able to collect electrical signals from the brain. But if you end up with something like this, where all these initials are basically electrodes that are being put on the scalp. And the scale is over here is from 0 to 500 milliseconds. So you have 500 milliseconds of data, and all these squiggly lines represent a value, an amplitude in terms of microvolts. So your data is basically in terms of microvolts by milliseconds. And how do you end up from the time domain, which is measured, microvolts by milliseconds? How do you end up in the frequency domain? How do you extract alpha waves and beta waves from this from this image of just what appears to just be squiggly lines in terms of a millisecond scale? And so to do that, you basically have to shift from the time domain to the frequency domain. And to do that, we use something called the Fourier Transform. So the Fourier Transform is this mathematical function that enables the switching between different domains, namely time and frequency, and back again from frequency to time. And the function itself is quite complex, and I don't think it's necessary to understand mathematically exactly what is happening. But I think this channel on YouTube gives a fantastic explanation and an animation that will really help understand what exactly is happening at a theoretical level. So let's watch this for 10 minutes, and I'll continue on after that.
This right here is what we're going to build to this video, a certain animated approach to thinking about a super important idea from math, the Fourier transform. For anyone unfamiliar with what that is, my number one goal here is just for the video to be an introduction to that topic. But even for those of you who are already familiar with it, I still think that there's something fun and enriching about seeing what all of its components actually look like. The central example to start is going to be the classic one, decomposing frequencies from sound. But after that, I also really want to show a glimpse of how this idea extends well beyond sound and frequency into many seemingly disparate areas of math and even physics. Really, it is crazy just how ubiquitous this idea is. Let's dive in. This sound right here is a pure A, 440 beats per second, meaning if you were to measure the air pressure right next to your headphones or your speaker as a function of time, it would oscillate up and down around its usual equilibrium in this wave, making 440 oscillations each second. A lower pitch note, like a D, has the same structure, just fewer beats per second. And when both of them are played at once, what do you think the resulting pressure versus time graph looks like? Well, at any point in time, this pressure difference is going to be the sum of what it would be for each of those notes individually, which, let's face it, is kind of a complicated thing to think about. At some points, the peaks match up with each other, resulting in a really high pressure. At other points, they tend to cancel out. And all in all, what you get is a wave-ish pressure versus time graph that is not a pure sine wave. It's something more complicated. And as you add in other notes, the wave gets more and more complicated. But right now, all it is a combination of 4 pure frequencies. So it seems needlessly complicated given the low amount of information put into it. A microphone recording any sound just picks up on the air pressure at many different points in time. It only sees the final sum. So our central question is going to be how you can take a signal like this and decompose it into the pure frequencies that make it up. Pretty interesting, right? Adding up those signals really mixes them all together. So pulling them back apart feels akin to unmixing multiple paint colors that have all been stirred up together. The general strategy is going to be to build for ourselves a mathematical machine that treats signals with a given frequency differently from how it treats other signals. To start, consider simply taking a pure signal, say with a lowly 3 beats per second, so that we can plot it easily. And let's limit ourselves to looking at a finite portion of this graph, in this case the portion between 0 seconds and 4.5 seconds. The key idea is going to be to take this graph and sort of wrap it up around a circle. Concretely, here's what I mean by that. Imagine a little rotating vector where at each point in time, its length is equal to the height of our graph for that time. So high points of the graph correspond to a greater distance from the origin, and low points end up closer to the origin. And right now, I'm drawing it in such a way that moving forward 2 seconds in time corresponds to a single rotation around the circle. Our little vector drawing this wound up graph is rotating at half a cycle per second. So this is important. There are two different frequencies at play here. There's the frequency of our signal, which goes up and down 3 times per second. And then, separately, there's the frequency with which we're wrapping the graph around the circle, which at the moment is half of a rotation per second. But we can adjust that second frequency however we want. Maybe we want to wrap it around faster, or maybe we go and wrap it around slower. And that choice of winding frequency determines what the wound up graph looks like. Some of the diagrams that come out of this can be pretty complicated, although they are very pretty. But it's important to keep in mind that all that's happening here is that we're wrapping the signal around a circle. The vertical lines that I'm drawing up top, by the way, are just a way to keep track of the distance on the original graph that corresponds to a full rotation around the circle. So lines spaced out by 1.5 seconds would mean it takes 1.5 seconds to make one full revolution. And at this point, we might have some sort of vague sense that something special will happen when the winding frequency matches the frequency of our signal, 3 beats per second. All of the high points on the graph happen on the right side of the circle, and all of the low points happen on the left. But how precisely can we take advantage of that in our attempt to build a frequency unmixing machine? Well, imagine this graph as having some kind of mass to it, like a metal wire. This little dot is going to represent the center of mass of that wire. As we change the frequency and the graph winds up differently, that center of mass kind of wobbles around a bit. And for most of the winding frequencies, the peaks and the valleys are all spaced out around the circle in such a way that the center of mass stays pretty close to the origin. But when the winding frequency is the same as the frequency of our signal, in this case 3 cycles per second, all of the peaks are on the right and all of the valleys are on the left, so the center of mass is unusually far to the right. Here, to capture this, let's draw some kind of plot that keeps track of where that center of mass is for each winding frequency. Of course, the center of mass is a two-dimensional thing. It requires 2 coordinates to fully keep track of, but for the moment, let's only keep track of the x-coordinate. So for a frequency of 0, when everything is bunched up on the right, this x-coordinate is relatively high. And then as you increase that winding frequency, and the graph balances out around the circle, the x-coordinate of that center of mass goes closer to 0, and it just kind of wobbles around a bit. But then, at 3 beats per second, there's a spike, as everything lines up to the right. This right here is the central construct. So let's sum up what we have so far. We have that original intensity versus time graph, and then we have the wound up version of that in some two-dimensional plane. And then, as a third thing, we have a plot for how the winding frequency influences the center of mass of that graph. And by the way, let's look back at those really low frequencies near 0. This big spike around 0 in our new frequency plot just corresponds to the fact that the whole cosine wave is shifted up. If I had chosen a signal that oscillates around 0, dipping into negative values, then, as we play around with various winding frequencies, this plot of the winding frequency versus center of mass would only have a spike at the value of 3. But negative values are a little bit weird and messy to think about, especially for a first example, so let's just continue thinking in terms of the shifted up graph. I just want you to understand that that spike around 0 only corresponds to the shift. Our main focus, as far as frequency decomposition is concerned, is that bump at 3. This whole plot is what I'll call the almost Fourier transform of the original signal. There's a couple small distinctions between this and the actual Fourier transform, which I'll get to in a couple minutes, but already you might be able to see how this machine lets us pick out the frequency of a signal. Just to play around with it a little bit more, take a different pure signal, let's say with a lower frequency of 2 beats per second, and do the same thing. Wind it around a circle. Imagine different potential winding frequencies, and as you do that, keep track of where the center of mass of that graph is, and then plot the x-coordinate of that center of mass as you adjust the winding frequency. Just like before, we get a spike when the winding frequency is the same as the signal frequency, which in this case is when it equals 2 cycles per second. But the real key point, the thing that makes this machine so delightful, is how it enables us to take a signal consisting of multiple frequencies and pick out what they are. Imagine taking the two signals we just looked at, the wave with 3 beats per second and the wave with 2 beats per second, and add them up. Like I said earlier, what you get is no longer a nice pure cosine wave, it's something a little more complicated. But imagine throwing this into our winding frequency machine. It is certainly the case that as you wrap this thing around, it looks a lot more complicated. You have this chaos and chaos and chaos and chaos, and then whoop, things seem to line up really nicely at 2 cycles per second. Then as you continue on, it's more chaos and more chaos, more chaos, 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 whoop, things nicely align again at 3 cycles per second. And like I said before, the wound up graph can look kind of busy and complicated, but all it is the relatively simple idea of wrapping the graph around a circle. It's just a more complicated graph and a pretty quick winding frequency. Now what's going on here with the two different spikes is that if you were to take two signals and then apply this almost Fourier transform to each of them individually, and then add up the results, what you get is the same as if you first added up the signals and then applied this almost Fourier transform. And the attentive viewers among you might want to pause and ponder and convince yourself that what I just said is actually true. It's a pretty good test to verify for yourself that it's clear what exactly is being measured inside this winding machine. Now this property makes things really useful to us because the transform of a pure frequency is close to 0 everywhere except for a spike around that frequency. So when you add together two pure frequencies, the transform graph just has these little peaks above the frequencies that went into it. So this little mathematical machine does exactly what we wanted. It pulls out the original frequencies from their jumbled up sums, unmixing the mixed bucket of
Okay, great. So I hope that was really helpful in understanding kind of how the Fourier transformation works and giving you an intuition into what is going on. Honestly, I myself am not familiar with the math behind that, and every time I watch this video, I feel like I come away with a better foundational understanding of how exactly we go from going into dealing with electrical signals in terms of microvolts per milliseconds and transforming that into frequencies. So with the help of the Fourier transformation, we're able to decompose these electrical signals into the 4 kinds of frequencies we were looking at earlier. But once we have frequencies, how do we interpret frequencies? Or what is a way we can plot frequencies to understand how exactly frequencies are changing as a function of time? So that brings us to PSD plots, and PSD stands for power spectral density. This graph allows us to analyze the magnitude of frequencies within a given time frame. So let's kind of break down what we're looking at over here. Each individual line that you see in this graph corresponds to an electrode on the subject scalp. So each line is one individual electrode, and oftentimes when you collect EEG data, you often use 32 electrodes or 64 electrodes. So it looks like we could easily have 64 individual lines, meaning 64 electrodes. You'll see that the x-axis notes frequency in hertz. So this particular graph is showing this frequency ranges from 0 to 30 hertz. So we cover all the way from delta, which is a 0 to 3 range, all the way to, I think, beta, I believe, which would be 13 to 30 hertz. The y-axis is interesting. The y-axis says log power, and you have the units of decibels per hertz. So we measure frequencies in the units of power, right? As I said before, what matters is not whether the frequency is present. It's not 0 or 1. It's the extent to which it is present. What is the power of this frequency? How strong is it? And so we measure the power in this logarithmic scale, and the details of why this scale and how exactly to interpret these values is not as important as much as visually seeing where the power or magnitude of each frequency increases. So over here, we see a wide consensus across all of these individual electrodes that there's a peak in power from 7 to 13 hertz, which is exactly the range that the alpha wave band is. So let's say that you heard someone, or you heard a doctor, or you heard a researcher saying that they had high alpha band activity, or they witnessed an increase in alpha power during such and such experimental task. This is what a PSD plot for such a scenario would look like. Relatively, compared to everything else, the alpha power range, or the power within that frequency range, is higher than everything else. And that's why we can deduce that there's higher alpha band activity. So let's say we have something like this, but we don't want the filter, we don't want that particular frequency range. Or better yet, let's say we are trying to make a brain-computer interface that can control a mouse cursor for you. It can, just by thinking about whether you want to move up and down, left or right, it can control that for you. For that particular task, you're looking at motor imagery, right? You are basically thinking of up, down, left, right commands, and you want the device to interpret, you want the machine learning model to recognize that for you and move the cursor accordingly. So because you're looking at motor imagery commands, you're really only caring about the frequencies elicited from the motor cortex, or in a particular range, such as the mu or the beta frequencies. In that case, if you are trying to isolate a particular frequency range, what are some things you could do? That leads us to filtering. So filtering allows us to selectively remove or select for frequencies. So it's useful when you're trying to isolate frequencies and choose features. There are a couple of different types of frequencies, the names of which might be hard to understand at first, but once you get the hang of it, it's really not that bad. So the first is the low-pass filter. The low-pass filter basically allows frequencies below a certain threshold and removes everything else. So the way I like to understand it is it's a low-pass filter passes anything that is lower than that value. So let's say I implemented a low-pass filter at 30 hertz. Anything that is less than or equal to 30 is included, and then anything 30 or anything above 30 is gradually phased off or removed entirely. The high-pass filter works similarly, but in the opposite way. So frequencies higher than a certain threshold are kept, and anything lower than that is removed. So again, a 30 hertz high-pass filter will pass anything that is greater than or equal to 30 hertz and remove anything that is less than or equal to 29 hertz. A bandpass filter passes frequencies between a certain range. So a bandpass filter of 15 to 30 hertz will preserve frequencies between that range and phase out anything that is not within that range. And a notch filter is targeting a specific frequency. So it can be 60 hertz, it can be 50 hertz, it can be 35 hertz, but it'll only target that specific frequency range, and usually use a notch filter to selectively remove a desired frequency. So let's look at some examples. Here's the PSD plot of a particular subject. You can see each line reflects an electrode, so you have a lot of colorful lines in this, which you can basically think of as one particular electrode. And we have frequency ranges at the x-axis from 0 to 60 hertz, and we have the magnitude or the power. This is a different unit scale than we saw earlier, but we have basically the y-axis is a power scale. So what do we notice here right off the bat? We have all the frequencies look relatively normal. We have a peak in the 7 to 13 hertz range. Excuse me. So we have a peak in the 7 to 13 hertz range, and we have a giant peak in power at 50 hertz. And this peak right here is way higher than everything else, which usually when you see something like this in the data set, it's a sign that it's something unusual. In fact, this particular notch, or this particular peak at 50 hertz, is indicative of the recording equipment in the room. So in the UK, or I think in Europe in general, all of the electrical devices operate at 50 hertz. So when you're collecting EEG data, the data recording systems are so sensitive that they'll also pick up the electrical activity of other devices in the same room. So because you might have other electrical devices such as your phone or your computer that's plugged in, or even the battery pack or lights for that matter, everything is oscillating at 50 hertz. And so you notice a gigantic magnitude at that time. If you were recording in the US, you would also notice the same thing, but it would be at 60 hertz. So they had their international differences and codes for which at what frequency all the electrical devices operate at. But you have depending on where you are, you'll notice some things like this. So let's say we want to remove this. What would be the best filter to choose for this scenario? And the correct answer for that would be the notch filter, because there is no frequency range in this case. There is no threshold such as higher, greater than, or less than a particular frequency value. It's really just this one thing at 50 hertz that we want to selectively remove. And so we would use a notch filter to do that particular task. We can look at another example as well, which hopefully will give you more intuition into how frequency works and how to really interpret this PSD plots. So again, we have another PSD plot. Similar to everything else, each individual line refers to an individual electrode. So you can see here on the map, like which line corresponds to which position of the electrode. And these are the two ears, and this is the nose of the subject. So you can kind of orient yourself and understand where the electrode is positioned and map that to the corresponding PSD activity that you're seeing. So let's try to break down what is happening in this graph right here. You have a frequency range from 0 to 70 hertz that is depicted, and again, a power spectrum from what looks like 60 to 150 decibels. So in this case, we have basically implemented a low pass filter of 30 hertz. So you see there's a cutoff here at 30 hertz, and everything that is lower than 30 looks to be untouched. And then as soon as we cross 30, there's a gradual phase off, and then everything else is almost silenced or muted. So all these frequencies have been muted, and there's a gradual fall off period between, let's say, 30 to 35 hertz, in which it tapers off, and then it's kind of dampened from there on out. And so that is effectively what a filter does, especially a low pass filter. It'll take something, and let's say our threshold was 30 hertz. So it'll say anything less than or equal to 30 can pass, anything lower than 30 can pass. That's why it's called a low pass filter. And then anything above that is gradually phased off or filtered out. And so filtering in general allows us to do a lot of signal processing and isolate frequencies such that we only keep what is necessary and remove any extraneous noise. EEG data is very noisy to begin with, so steps like these help us to clean the data even more, which helps in the accuracy in building a brain-computer interface. So we'll get to that slide in a bit. But as a bit of a recap, we covered the basic frequencies. There's alpha, there's beta, there's theta, and there's delta. There are also other frequencies. These are kind of like the colloquially referred ones that are referred to, the ones that are most commonly known. And we covered, how we go from collecting electrical data to looking at frequencies using the Fourier transformation. And after we get the frequencies, how to analyze that using the PSD plot and what kind of filters are applicable and what they do. Please, so that is essentially the end of our second module. Please do check out our website, or email us if you have any questions about this content in particular. Whether you are from Davis or not, we'll be happy to answer any questions and help out the best we can. The next video we'll publish is an interactive walkthrough in Python on how to implement these signal processing techniques and how to plot them and look at them in a Jupyter notebook. So stay tuned for that.